yesterday we were talking about the principles of uniform circular motion. Right? So just a quick review. If something's going to move in a circle, it's because it is constantly doing what? Being pulled towards the center. So there is a net force acting towards the center of the circle. Okay? We call that what kind of a force? Centripetal. Okay? Centripetal force causes a centripetal acceleration. Okay? Now that acceleration isn't making the object moving in the circle go faster because it's actually traveling at a constant speed. The acceleration is merely changing the object's direction of travel, which is why it travels in a circle. Okay? It is constantly changing direction. All right, so what we saw yesterday was that according to a diagram like this, if that centripetal force suddenly disappeared, the object would travel in a straight line, tangent to the circle wherever the force disappeared. Okay, travel in a straight line from there. Okay, and that's where we talked about the whole David and Goliath thing, and then we couldn't watch the video because it didn't work, and I couldn't find it. I looked last night, okay, and it's been taken down for copyright purposes like everywhere. Okay, so unfortunately, I'm not going to show that one. Okay, so we're going to look at the effect of radius on centripetal acceleration. So yesterday we said the formula for centripetal acceleration is v squared divided by r. Right? And we said that the faster an object moves in a circle, the greater the acceleration will be, linearly or exponentially? Exponentially. Okay. An increase in radius will cause the centripetal acceleration to decrease linearly because r is not squared. Okay? So if I double my radius, what should happen to my centripetal acceleration? It will be cut in half. Right? This is an inversely linear relationship. The bigger r is, the smaller AC is. All right, so we're going to look at that here with this example. So we've got the same car going around two different corners. Okay? It's going to go around both of these corners at the same speed, 28 meters per second. So v is going to stay the same. R is going to increase. So in our first situation here, okay, if we want to calculate the centripetal acceleration, we're going to take v squared, 28, and divide it by the radius of the circle, 320. Okay, so our centripetal acceleration here will be 28 squared divided by 320. Okay, so we get a centripetal acceleration of 2.45 meters per second squared. Okay, to give you an idea, okay, just for like curiosity's sake, most production vehicles can withstand a centripetal acceleration around 7 to 8 meters per second squared. Okay? Does that mean it would be comfortable for the occupants of the car? No. Okay? Really high-end sports cars, they can actually accelerate around a corner at close to 9.81 meters per second squared, which means if you were thrown against the door would push on you with a force equal to your own weight. Okay? If you were in a really high-end sports car cornering at its maximum ability. Okay? Obviously, we don't want to do that all the time for a couple of reasons. It's unsafe and uncomfortable for your occupants, and we're relying on what force to keep us there? Friction. Is that constant? No, it's quite variable, and you don't want to depend on it. Okay? All right. Centripetal acceleration for this second corner. It's much wider. I'm still taking it really fast. 28 meters per second is really fast. Okay? But is the acceleration going to be bigger or smaller? Yeah, smaller. How much smaller? Well, the first corner is 320. The second corner is 960. It'll be 1/3. Okay? Because the second corner has a radius 3 times greater than the first corner. Right. So our centripetal acceleration for this corner will be 28 squared divided by 960. Okay. So we're getting an acceleration there of 0.816 or 817 meters per second squared. that would be much more pleasant for the occupants of the car. They wouldn't feel like they were thrown into the door or be grabbing onto the holy crap bar there on the C-pillar, hanging on for dear life. Okay? Or if you're like a buddy of mine in high school, just fall out the door of your Jeep. Well, because there was no door. Okay? Because Jeeps do that for some reason. You can take the doors off. It really doesn't make a lot of sense. Of course, he wasn't like a seat. He was an idiot. But no, luckily we weren't going all that fast. He just wasn't wearing a seatbelt and wasn't paying attention. My buddy just cranked over on the wheel and out the door he went. Luckily it was in a parking lot, so he was just being stupid. Yeah. You're still young. Don't be stupid. Stuff like this. All right, so just to be sure here, we said that this should be 1/3 of that number. And it is. Okay, so we're good with that relationship then. Okay. So that's what we just did. Okay, we did that calculation. We can see clearly that radius has an inversely linear effect on centripetal acceleration. Okay, so we are going to skip ahead here now to centripetal force. Okay, so this lesson here, guys, we're going to look at not the acceleration, but now at what kinds of forces can act as centripetal forces. Okay, anything that can pull an object or push an object towards the center of a circle constantly can act as a centripetal force. Okay, friction is a very common centripetal force that we use when we turn. Right? What's another very common centripetal force? Gravity. Gravity, absolutely. Okay, the moon wouldn't orbit the Earth wouldn't orbit the sun, and so on, if it wasn't for gravity acting as a centripetal force. So gravity is a very common centripetal force. So is tension. Okay, if you tie a string to something and whirl it around and around, tension acts as a centripetal force. Okay, so circular motion cannot occur without a force pulling into the center. Okay, there has to be a net force pulling into the center. Okay, lots of forces can act as a centripetal force. They are centripetal forces. We're going to look at how they operate, and then we're going to look at the two kinds of curves: unbanked curves, unbanked corners, and banked corners. Okay, now where do you see banked corners? NASCAR has really steeply banked corners. Yes. Where else? Skeleton, bobsled. Those are banked corners. Yes. Okay. Mario Kart does have a couple of banked corners. Indoor biking. Yeah. Okay. If you got the indoor cycling stuff, they've got those banked corners too. Okay. You guys are missing one that you use all the time. On and off ramps. Okay. Any interchange. Okay, a highway interchange of any kind is always going to use a banked curve. Right? Banked curves are excellent for doing two things: reducing the amount of space needed for the interchange and increasing safety. Okay? Because banking a curve means we don't have to rely on friction to provide the centripetal force for that corner. We can rely on the bank of the corner to push us back. So we don't have to rely on friction nearly as much. Okay, so Newton's second law says that a net, well, let's see if we can see, a net force is calculated by multiplying mass times acceleration. Now, the same is true for something going around and around in a circle. All that changes is this isn't a regular acceleration, this is what kind of acceleration? Centripetal. Okay, so then we would be saying mass times centripetal acceleration equals our net, or in this case, centripetal force. Now, we have a formula for AC. Yeah. Okay, we just used it. What is it? It's V squared over R, which means to calculate centripetal force, we go mv squared over R. That's still m times a, but now it's the circle. That will be your most important formula in this unit. Okay? You will use it like you used m times a in the last unit, basically all the time. Okay? Now, the other thing we got to realize here is that centripetal forces work just like other forces. Fc is really also the vector sum of all forces. But it's a lot easier because there's only going to be two vectors. in the circle, out of the circle. Okay, no more of these angles and north and west and whatever else. Okay, you really only have these two forces, and most of the time we don't have any forces out of the circle. Okay, there'll be a few situations where we do, but for the most part, we're just looking for the force that is providing the centripetal force. Okay, it's usually going to be just one force. Okay. So, in some cases, it's easy to identify what's keeping an object in the circle. Okay, when I whirl around the roll of tape, okay, it's pretty easy to determine why it's moving around the circle. It's because, there's a string on it. Okay, so that keeps it in a circle. I'm only close. So it's obviously the string there. Okay, but in some cases it's not as easy. Like when you see a car go around the corner, you don't really see friction. Okay, it's there, but it's not really something we can observe. Okay, but it is the force providing the centripetal force for an object going around an unbanked corner. Okay. All right. So if I'm looking at the effective speed on centripetal force, so again, I'm looking at this formula here, mv squared over r. Okay? According to this formula, any increase in v will cause what for Fc? To increase exponentially. Okay? Because I'm multiplying by v. And if v gets bigger, it's also squared. So its effect is exponential. Okay? So if I double my speed, I will need 4 times the centripetal force in order to keep me in a corner or doing whatever I was doing. Okay, r, same as with acceleration, if I increase r, Fc will go down. Okay, and it'll go down linearly. So if I double r, Fc will be cut in. All right, so if we're looking at this, then we can prove that we have this plane that's 0.9 kilograms, and we're looking for the tension in the string for speeds of 19 and 38 meters per second with a 17-meter line. In other words, our radius is 17 meters. Okay, so in situation 1, okay, we have our 0.9 kilograms times 19 meters per second squared, okay, divided by, 19, sorry, the 17 meter. Okay, all right, 17. Okay, so if we do that, 0.9 times 19 squared divided by 17. All right, so we're looking at 19.1 newtons worth of centripetal force. Okay. If I double that speed to 38, I should need how much more? 4 times. Okay, let's just confirm that that's actually what happens here. So 0.9 times 38 squared divided by 17. Okay, 76.4. Does that look like 4 times more? Yep. Okay, so we're right on that relationship. Yep. Okay, everybody all right with that idea? Okay, so that's what we just did there. Okay. All right, effective radius on centripetal force. Is it going to be the same as the effective radius on centripetal acceleration? Yes, it is. Okay, because they're part of the same thing. Right. So we're looking for the tension in the lines for lengths of 11 and 22 meters if they're always moving at 28 meters per second. All right, so for our first one here, we're going to have the same plane, 0.9 kilograms times 28 squared, okay, divided by 11 meters. Okay, so 64.1. Okay, so when I double the radius in this situation, my FC should go down by how much? By half. It should be cut in half. I'm going to have twice the radius. I should have half as much force. 0.9 times 28 squared. Okay, exactly half. 64 and 32. Everybody okay with those relationships? Okay. So the tricky part, okay, with centripetal force is really determining what's acting as a centripetal force. Most of the problems that we solve in this unit, okay, are going to involve us doing this. Setting FC equal to some other force. Maybe it's gravity, okay? Maybe it's friction, okay? If that's the case, then it's going to be mv squared over r equals m times g. Or if it's friction, then it'll be mv squared over r equals mu times the normal force, okay? We're always just going to be setting the net force equal to the sum of all forces. It's just that most of the time there's only going to be one force. Okay? All right. So, looking at unbanked corners here. Okay? When a car moves at a steady speed around an unbanked curve, or just a regular corner, the centripetal force keeping it in the curve comes from the static friction between its tires and the road. Static friction. Right? If you start to slide, what kind of friction are you relying on? There's two kinds of friction, static and kinetic. Which one was always bigger? Static. Okay? Static friction is always bigger. If you start to slide, then you're relying on kinetic friction. And you are not going to be able to get as much friction to keep you in the corner, and you'll slide out of it, okay? Or wider. It'll take you longer to go around. So this is usually where people say, yeah, but Coderre, if you drift a corner, you can go around the corner faster. Actually not true, okay? Mythbusters actually did a whole episode where they brought the Drift King over from Japan, and they made a track. They drove this like Ford Crown Victoria, like the old police cruisers, okay, around this track. They both, Jamie and Adam, drove it around the track as fast as they could without skidding. Then they brought the Drift King in, and he went around, and he couldn't beat their time. He looked way cooler. Okay, make no mistake, when he was drifting every corner and going around, he looked way, way cooler. But because he was always sliding, he wasn't going around the corners as quickly. Okay, certainly he was able to accelerate a little better getting into the straight parts, but okay, he couldn't get around the corners as fast because he would slide out and around. Okay. Now, if you're wanting to drift a corner, what do you have to do with your car? You got to hit the e-brake so that your back tires go out like this. So a car normally going around the corners relying on static friction, which is doing this, working directly back towards the center. When you're drifting a corner, you're putting the back end out like this. Okay? And your tires are spinning and exerting a force this way. It's not directly back towards the center. Okay? You see how that arrow doesn't point exactly towards the center? It certainly has a component that points towards the center, but it also has a component that points that way, which is why it's not as effective at getting you around the corner. Okay? You're not using as much force in the right directions. Okay? The only advantage to drifting is if you're going to have a straight coming up and you're going to have some momentum in the wheels. If they regain traction, they'll already be moving faster than a car that was going around. Okay? And so you'll be able to accelerate down the next straight a little bit more quickly. Right? So, depending on the situation, but in most situations, drifting is going to be slower going around the corner than taking a corner, which is why you never see Formula One, NASCAR, or any professional racers drifting corners. Okay? If it was faster, all the racers would do it. Okay? It's quickly not fast. Follow me there? All right, so we're relying on static friction. Okay, so as a person goes around a corner, okay, the car wants to do this. Okay, obey Newton's first law. Okay, that's what the occupants of the car want to do as well. Okay, they want to travel this way, but the car changes direction. And so they try to travel that way, and they feel a push on the door, okay, or their seat belt that's pushing or pulling them back towards the center. right? And that is all provided by the static frictional force between the tires and the road. If that force disappears or decreases significantly, then the car will obey Newton's first law and continue to travel in a straight line. Okay, so let's have a look at the effect of friction on how fast you can take a corner. Right? So we're going to compare the maximum speeds at which a car can safely negotiate a regular unbanked corner, okay, in dry weather, where the coefficient of friction is 0.9, and icy weather, where the coefficient of friction is 0.1. Okay? Ice very quickly decreases the coefficient of friction. Okay? This is 1/9 the amount of friction available on a dry road. Okay? So very, very major decrease. Okay, so we just said that to go around an unbanked corner, centripetal force is being provided by friction. Okay. The formula for centripetal force is mv squared over r. The formula for the force of friction is mu times the normal force. Since this is an unbanked corner, that means it's level. The normal force is equal to what force? Gravity. Okay, can I calculate how fast the car can negotiate this corner? I have to isolate what? Not M. V. Yeah, I'm trying to figure out how fast it can go around the corner. V is how fast. You want to follow me on that? Okay, so I want to isolate V. So I'm going to take R, I'm going to multiply it over here. Then I'm going to divide both sides by M. What's going to happen? M will cancel. Same car off both sides. Okay, and I'm looking for V, not V squared, so square root. All right, so V will equal the square root of mu. You'd be surprised how often that actually comes up. Like how often the square root of mu is actually the formula. Okay, suppose. All right, so if I've got that formula, then I can calculate V. Mu for the dry road was 0.9 multiplied by 9.81 multiplied by the radius of the corner, which was 50 meters. So that car can take that 50-meter corner at 21 meters per second under ideal dry conditions. Okay. What do I do differently to calculate V for the slippery? Yeah, I just changed mu to 0.1. Right? So V for the icy part will be 0.1 times 9.81 times 50. Right? Remember, this all started with us realizing that the centripetal force was being provided by the force of friction. That's something you just need to memorize. Okay? In an unbanked corner, friction equals centripetal force. Okay? It's providing the centripetal force. All right, so for the icy corner, how much slower do you think we're going to go? We got 1/9 the amount of friction. How much are we going to have to slow down? How much? Okay, it's exponential, but it's square rooted. What's the square root of 9? Okay, so we'll have a look here. Square root of 0.1 times 9.81 times 50. Okay, we have to go 3 times slower if we have 1/9 the available friction. Okay, so we have to go 7 meters per second. Okay, so for an unbanked corner, friction provides the centripetal force mv squared over r equals mu at n. Okay, always going to be that way for an unbanked corner. Okay. Did everybody make a note of that? Unbanked corners. This is the formula. Probably should. Okay, I'm going to give you a 5-minute break before I go on to unbanked curves, because unbanked curves get a little hairy. Okay, Next type of curve we want to look at are banked curves. Right? So a banked curve, by definition, is not level. Okay? It's tilted. In effect, it's an inclined plane. Okay? That's really all a banked curve is. Okay? So when we have something sitting on an inclined plane, okay, we've got some other forces that are working for us. Okay? Some of the bank, or some of the corner, the flat surface of the road, okay, is going to exert a force out from the road. Okay? So that's going to look like this. Okay? So we have the car on the corner, which, like we said, is an inclined plane. Okay, like this. There's going to be the force of gravity acting down, and then there's going to be some other forces, one of them being normal force. Now, normally on an inclined plane, we just have the object sitting there, and it's either sliding down or being pushed up. But because this is going around the curve, the car has some inertia, and that inertia is going to cause it to do what as it goes around the corner? Want to go up the ramp and slightly into the ramp. If it pushes on the ground, what does the ground have to do? Push back, which is why we don't use the usual inclined plane triangle where Fn is smaller than Fg. We're using this one. Fn is going to be a little bigger than Fg now because we've got a little bit of push from the car pushing on the road. Okay, so we've got Fn now being the hypotenuse of the triangle. And then we've got this force here, acting straight up. Since the car is not moving up or down, this straight up force has got to be equal to a downward force, which is gravity. Okay? And then, across the top, we have a force that's directed towards where? Towards the center. Usually we call forces that are directed towards the center centripetal forces. Okay, so this side of the triangle is going to be providing us with the centripetal force. So we don't have to rely on friction here. Okay, friction is going to be involved. Okay, it's there, but we don't have to rely on it. If I had a bank curve covered in perfectly frictionless ice, there is still a speed I could take it at where I wouldn't slide in or out of the bank curve. Okay. Well, you would have to be, well, you wouldn't be keeping any acceleration. I would come into the corner at that speed. Since the ice is frictionless, it can't slow me down, and I would just go around the corner at that recommended speed. Okay? So all bank curves are designed to effectively have a safe speed that you can traverse them at, regardless of the road conditions. Okay? So even if that bank curve is covered in really, really slippery ice, if you take it at the recommended speed, you will be safe. Here's the problem. Some people get overly cautious. And if that bank curve, that thing is covered in really slippery ice, they go, oh, 40 is kind of fast, even though that's the recommended speed. I'm going to go 30. What happens to them? They slide in. It's just as dangerous on a really slippery bank curve to go too slow as it is too fast. Okay? You go too fast, you slide out. Go too slow, slide in. I've actually seen it happen. Okay? Back before they started doing all this 22X stuff there, where McLeod and 22X used to cross, there was a curve you would go around to go onto the McLeod Trail northbound from Highway 22. It was a tight corner and it was banked pretty well. And I was coming onto that, and the person in front of me was slowing down, and I'm like, oh crap. What do? I'm behind this person. If I slow down, I know what's going to happen. I'm going to slide into the middle. Okay? So I try and get outside of them, which means I have to speed up a little bit. So I start drifting towards the outside. Meanwhile, the person who's in front of me is slowing down so much that they're actually starting to slide in. And of course, by the time they realized that's what was happening, it was too late. It's not like they can put on the power and speed up. The ice is really slippery. So what ended up happening is their front wheels are spinning like mad, because it's a front wheel drive car, and they're sliding right into the middle. Meanwhile, I was able to slow down by backing off, okay, and staying at the right speed as I went around. Laughing all the way, because physics rocks, and that person didn't understand it. Okay? Physics rocks. Because physics can make you look really smart, and other people really stupid. Okay? If you stop it, no. No! You go too slow? Search you in the middle. I had to get to work. Too busy. Right? Physics waits for no one. So, either you understand how a bank curve works, or you call a tow truck from the middle of the turn. Get you. Okay. Yeah, when stuff like that happens, I don't know. Can't fix stupid. Okay. So you should also never argue with an idiot. You know why?
They can't be convinced.
No, they'll drag you down to their level and beat you with experience. True story. Okay. All right. So with this bank curve, okay, what we have is an interaction of a number of forces, but that interaction produces a slight amount of force directed towards the center. Right. So that's what we're going to look at is those directed forces. A plane also uses this principle in order to turn. Okay. If you've ever been on a plane, when a plane wants to turn, it dips the wings. Okay. It doesn't just fly flat and do this. It's not a boat. Okay. A boat can do that, but a plane can't. Okay. A plane has surfaces on the wings that produce lift. Right. That produces an upward force. If the plane wants to turn, what it needs to do is bank so that some of that lift now has, instead of pushing straight up, it pushes at an angle, which has a horizontal component directed towards the center of the circle. Okay? Now, the issue with turning like this is that you've lost some of your lift. So what does the plane do while it's turning? It reduces altitude. That's why right before you land, the plane usually does this a little bit. Okay? Flies in kind of a circle a few times, okay, to lose altitude and slowly get down to the landing altitude. Okay? So banking the wings will result in a loss of lift, which will result in a descent as well as a turn. Now, is there a way to possibly prevent the loss of altitude? Not decrease the velocity, increase the velocity. Yeah, if you go fast enough, you probably could do it, but you're still losing some lift. Okay, you lose some lift, then you're going to lose some altitude. Okay, all right. Then you've got obviously your NASCAR bank corners. Okay, these corners are banked so steeply that when they want to pave them, the paving machine has to be held on with a crane because the paving machine will topple. Okay, and then slide down the ramp because they're banked so far. Okay, so what they actually do is they have a crane sitting outside the track holding the paving machine on, okay, so that it doesn't fall over. Okay, they're very, very steeply banked. Okay, so here's how we're gonna derive our banked curve formula, which incidentally is also on your formula sheet. Okay, so there's a formula that governs banked curves. Okay, that formula is this. The tan of theta equals b squared over r times g. Right now, that's just the end result. I'm just showing you where we're going. Okay? To show you how we get there. Okay? Basically, this formula says that the angle of bank, so how steep the corner is related to the speed, the radius, and gravity. Okay? Because gravity pulls the car into the corner. Okay? The radius influences essentially the tightness of the curve, and the speed influences how much you want to leave the corner. So the bank of the curve is influenced by those three things. All right. So if we look back at this, okay, we know that we have the normal force here, which is the hypotenuse, okay, and we have this force here, okay, and then we've got this force. They drew it down here. We're going to draw it up here. Okay, so this force is going to act as our centripetal force because it's directed back, and this force we said is going to be equal to the force of gravity. Okay, so Fc, this side here, is the opposite side to this angle, which is why they have it saying Fn times the sine of theta. Okay, so Fn is the hypotenuse, multiplied by the sine of theta gives me the opposite side. Okay, for this side here, which is equal to gravity, it's normal force times the cos of theta because it's the adjacent side. Everybody okay with that? So here's what we've got. Fc equals Fn times the sine of theta. So that means Fn times the sine of theta equals mv squared over r. This side of the triangle equals mv squared divided by r. This side of the triangle equals m times g. So Okay, so I'm going to take this out for right now. Okay, and I'm going to say that the centripetal force, okay, is the opposite side, and this is the adjacent side. So sine of theta divided by cosine theta. So that's opposite over adjacent. What's the trig function that handles opposite over adjacent? Okay, so what I'm really saying here is if I go opposite over adjacent, that's going to be the tan of theta. That's going to equal mv squared over r divided by m times g. If I divide those two things, what happens to m? Cancels, and I'm left with v squared divided by We're never going to be asked to derive that formula. Okay? I'm just showing you how we're supposed to. That's what we asked to do. Okay? Okay, so basically what they're saying is a bank curve is dependent on the opposite side and the adjacent side. Okay? It's dependent on gravity, and it's dependent on centripetal force. Okay? Does that sort of make sense? All right, so if we take those two things together, we can calculate that the angle of bank for a bank curve is equal to v squared over r times g. So v still has an exponential effect on the angle of bank. Okay? If I want to double my angle of bank, it's going to have exponential effect. Sorry, double my speed, it's going to have an exponential effect on how much I've got to bank the corner. Now, a bank corner can only be banked until it becomes vertical. We have to go pretty fast. Yeah, like really fast. If you wanted to stay on a vertical wall, okay, while going around in a circle. None of you have ever ridden a gravitron. Okay, like you can't eat. You get inside and it spins you really fast, so fast that you stick to the wall and can't fall down. That's that situation. How fast do you have to be spinning? Fast. Okay, so fast that that force, that your inertia basically has to make you push on the wall with a force equal to or greater than the force of gravity. That's how you don't fall.
Could you also just increase the radius?
Yes, you could. The tighter the radius, the slower that it would have to spin. All right, so this is the formula that city planners use, okay, or road designers use when they're designing an interchange, a proper interchange, not like the one there at like 162nd Street, right? The one that replaced one set of lights with four. Yeah. I don't know what was happening there, but there was clearly crack smoking going on. If nobody replaces one set of stoplights with four, it says it's a triumph of city planning. Okay. You guys know what I'm talking about, right? It's like this X, right? Yeah, the diamond interchange. They're raving about how the diamond interchange is brilliant. First off, the first time you go over it, you never get to the spot you want because it doesn't make any sense. You're crossing traffic like crazy, which is what an interchange is supposed to stop you from having to do, cross traffic, okay? But you do it anyway. And there's four sets of lights instead of one. It does have pretty lights on it. When you drive under it and you're not using it, you're just driving under it, it's awesome. As soon as you have to go over it, forget about it. Okay. A proper interchange consists of these things called clover leafs. They work really well. Calgary doesn't understand how those work. Okay? They sometimes make them and then they put lights at the top. Okay? If you design it properly, you don't need lights at the top. If you look at like Stony Trail, all the new interchanges on Stony Trail, none of them have lights at the top because they're actually designed the right way. Okay, the ones on Deerfoot, they're all messed up. They all have lights at the top. Okay, that's why if you want to get through Calgary, take Stony. Okay, it'll be faster almost all of the time, unless like 2 in the morning. Okay, so let's have a look at a couple of examples here of bank curves. Okay, so I want to determine the angle of bank. So this is what a city planner would be doing if they're designing an interchange. Okay, they want to figure out what angle they have to bank the road at if they want a speed of 35 meters per second, which is ridiculous. Okay? This is like 120 kilometers an hour. Okay, but they want to bank this curve for a speed of 35 meters per second and a radius of 550 meters. So we want to calculate the angle it has to be banked at. So here's our formula: the tan of theta, so the angle of bank, equals v squared over r times g. All right, so if we're looking at this here, we got 35 meters per second, so we got V, we got R, 550, and we always know what G is. So if we plug in those numbers, okay, that'll give us the tan of theta, which is 0.23. If I take the inverse tan of that, I get that this thing has to be banked at 13 degrees. Now you're probably looking at that number going, that's not that steep. That is steep. Okay? Really, really steep. Most roads will not have a grade of more than 8%. Okay? That's way more than that. Right? That means if you weren't traveling very fast, you would slide into the middle, even under pretty decent road conditions. It's really steep. And you would never bank something like this. Right? It would just be really uncomfortable to travel on. Okay, everyone follow how that formula works? Okay, now, could you be asked to manipulate that formula? Be given the angle of bank and asked to calculate the radius or the speed? Just a matter of manipulation. Okay, nothing difficult. Okay, we've already done stuff like that. All right, quick review here the other day. We talked about this relationship. Period equals 1 over F. What does F stand for? Frequency. Okay, so question number 1 here says the propeller of a toy airplane rotates at 300 rotations per minute. So that's a frequency, right? It's revolutions per time interval. They want the frequency in hertz. This is in revolutions per minute. We want to get it in hertz, which is revolutions per second. What do I divide that by? 60. Okay. Electric motor rotates with a frequency of 40 hertz. Okay. What's the rotational frequency in the RPMs? I would divide by 60. Okay. No, sorry, not divide by 60. I would multiply by 60. Okay. Sorry. All right, I want you guys to see if you can do that one. So you got a rock stuck in the tread of a tire, 36 centimeters, or 0.36 meters from the axle. It takes just 0.4 seconds for the wheel to make one revolution. What is the speed of the pebble at any instant? Okay, so we're given what in this question? Period. Okay, it says it takes 0.4 seconds to make one revolution. What else are we given? We're given the radius. Right, and we're being asked to find V. Do we have a formula that has those things in it? Okay.
Is that on the formula?
That is on your formula sheet, yeah. Okay, so V equals 2 pi over 2. We talked about it the first day of the unit here. Okay, so if I plug in my numbers here, 2 times pi times 0.36 divided by 0.4. All right, so this rock is moving at 5.7 meters per second as it goes around on the tire. Okay, so you're going to have to use all these formulas at some point. Okay, we've got to use those mv squared over r. We've got to use v equals 2 pi r over t, t equals 1 over f. Okay, that AC is v squared over r. They're all going to come up. We just have to recognize when we have to use each one. Okay, I want you guys to try these ones. Question number 1 is mostly about units, okay, making sure you have the right units. But you're looking for how much time it takes for the tires of a race car to make one revolution if the car is traveling at 261 kilometers per hour and the wheels have a radius of 0.350 meters. What do you have to do to the kilometers per hour? Make it meters per second. Okay. All right, give you guys a few minutes on those two, and then we'll go over them. So for our first one, like we said, the first thing we need to do is get the speed in meters per second. So we've got to divide our 261 by 3.6. All right, so now we've got our meters per second, 72.5. Okay, and we know that the radius is 0.350 meters. Okay, V equals 2 pi r over t. We're trying to find, okay, the period of one revolution. So I got to solve for t. So I'm going to multiply both sides by t, then divide both sides by v. So t will equal 2 pi r over v. So 2 pi times 0.350 divided by 72.5. Okay, so it's really small. Does it kind of make sense, though, for it to be really small?
Yeah.
Yeah. This thing's moving at 261 kilometers per hour. It isn't going to take very long for one rotation of the wheels to happen. Okay. If I wanted to know the frequency, what would I do with this number? Invert it, right. By going 1 over that number. Whoops. Okay, so that means that those wheels go around 33 times per second. Okay, is that a lot? But, I mean, it's going 260 kilometers an hour. Okay, that's pretty fast. All right, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star called a pulsar. Okay. It has a radius of only 16.1 kilometers and is spinning at a rate of 716 hertz. Okay, so imagine a collapsed star is spinning completely around once, like the Earth spins in one day. It's doing that 716 times per second. Okay, pulsars are weird. Okay, but they are like something incredible that actually exists in space. Okay, a collapsed star that spins at 716 rotations per second. Okay, so we want to find the speed at the equator. All right, so V equals 2 pi r over t, except we didn't get t, we got f. So instead of dividing by t, we could just multiply by f. Remember, f is 1 over t, right? This whole formula was already over t, so all I have to do is multiply by f. So I'm going to take 2 times pi times 16,100 meters. So you got to convert it from kilometers to meters. Okay, times 716. And when I do that, I'm going to get 7.24 times 10 to the 7 meters per second. Give you some idea, that is how fast light travels. Is that thing spinning pretty fast? Yes. It's like in terms of relativity, okay, if you were traveling that fast, time would slow down for you. Okay, your perception of time would slow down because you're traveling so incredibly fast.
Is the theory of relativity, like if you're traveling at the same speed as light, you would never age?
Not that you would never age, but you would certainly age differently because time is relative. Okay? Relativity works kind of like this. If I have a person walking beside train tracks at 2 meters per second, and I have a person on a train walking at 2 meters per second, which one looks like they're walking faster? Right. The one on the train. Because it's their speed plus the speed of the train, but relative, they're traveling at the same speed, right? But actually one looks like they're going faster. Okay? The same is true for time. As you increase in speed, your perception of time, or how time applies to you, changes. Okay? They even notice that when astronauts come back from the International Space Station, they travel fast enough, I mean not like anywhere near the speed of light or anything like that, but they're traveling very fast. They've been on the space station for a while, their watches will be off. Not by a lot.
Their watches be off, those are the same.
Because time is relative to speed, and they come back from being in orbit for a while, they've been traveling at a much higher speed than people on Earth have been, so the time has been different for them. It's only like a second or two, but it's enough.
But if you would take like a normal watch from here,
If I took 2 identical watches, set them, and sent one up to the International Space Station, left one on Earth, and after a year brought them back together, they'd be up. They wouldn't be the same
Keep
time.
the same, it's not about revolution, it's about speed.
Faster you go, the slower time goes.
Dude, like last year.
Crazy.
Dude. I just want
Okay, want you guys to try just before class ends here. Actually, we got time. Try number 1, okay? Number 1, super easy, centripetal acceleration question. Remember, our formula for centripetal acceleration is v squared over r. Okay? You will have to substitute in this question. We have a formula for v. It's 2 pi r over t. Okay, so you may have to do either one calculation first or substitute, which I'll show you in a minute. Okay, you guys can try that one first.